Welcome to this AP Chemistry Mastery Practice on topics 1.1 through 1.4. Let's go ahead and take a look at 3 questions today. The first one is a combustion analysis question. So we're given a compound containing carbon, hydrogen, nitrogen, and oxygen. And it was analyzed in the lab, and we have some data for this. Now, you can kind of scroll down a little bit and see that it says determine the empirical formula by the very end. So we're going to do a variety of different things to make sure we have that information. So the first thing we're asked is for the moles and mass of carbon. So we're given carbon dioxide, and we can use that to determine carbon. So 2.241 grams of CO2. Okay. Molar mass of carbon dioxide, I round to the whole number, so 44 grams per 1 mole of CO2. And then we can convert that into carbon. So we know that for every 1 mole of carbon dioxide, CO2, we have 1 mole of carbon. And in a combustion reaction, we can actually use this to determine moles of carbon. And so we go ahead and do the 2.241 divided by 44, and I go ahead and subtotal this on this one. It was asked for both, but even if you're determining the empirical formula, you may want both of them. So 0.05093 moles of carbon, okay? And then I'm going to go ahead and do that second step. Let me make that look like a 0 instead of a 0/6. So then to find grams, we're going to do for every 1 mole of carbon, of course, there's 12 grams of carbon. Okay. And we find that that is 0.6112 grams of carbon. So we just took care of both moles and mass of carbon. Now, for hydrogen, in this case, they gave us just grams of what hydrogen would be. If you had grams of water instead, you would do something similar to what we just did, but between water and hydrogen. But in this case, they just gave it to us. That was really nice of them. And so we're going to have 0.0648 grams of hydrogen that are in the sample. And then, of course, hydrogen is 1 gram for every 1 mole. And so this is going to be the same. Okay, so 0.0648 value, at least, same value, moles of hydrogen. Okay. All right, so in the next part, it's asking us to determine the amount of mass that came from nitrogen, and they give us a percent. So this is kind of an interesting scenario. So we're given a percent. We know that the original sample was 1.2359. And so what we can do is we can find the mass of nitrogen by multiplying the percent as a decimal times the sample. And so we'll do that. We're going to take 0.2884 for nitrogen. We're going to multiply that by the 1.2359 gram sample. And so we are going to end up getting a mass for nitrogen from that, and I subtotaled that already before I made the video, and I got 0.3564, and that's going to be grams of nitrogen. Okay. Now, if I want to know moles of nitrogen as well, of course, I'm going to have to go ahead and use the 14 grams of nitrogen for every 1 mole of nitrogen. So lots of just mole conversions between moles and molar mass. And I got 0.02545 moles of nitrogen. Now this is a tricky one. Sometimes they'll either only have nitrogen or only have oxygen. This one has both. So a couple different ways to solve the problem. Now we're going to look at how to determine the amount of oxygen. So we have a mass for, carbon, we have a mass for hydrogen, and we have a mass for nitrogen, which means the total amount that we started with has to be conservation of mass says that we should have the total amount that we started with, that we ended with. So we have to have that from oxygen. So we're going to take the 1.2359 gram sample, okay, so grams of the sample, and we're going to subtract from that the sum of those other masses. So we're going to have 0.6112 grams of carbon plus 0.0648 grams of hydrogen plus 0.3564 grams of nitrogen, and the only thing left is going to be how much oxygen we had. So when we subtotal this, we get 0.2035. Excuse me, my zeros are a little goofy there. Two. I will get this eventually. 2035 grams, and that's of oxygen. Now, we want to know moles of oxygen as well if we're going to do empirical formulas. So we're going to take that 0.2035 grams of oxygen, and of course, for every 1 mole of oxygen, there is 16 grams of oxygen. Okay. I'm going to actually switch colors to green for my oxygen, and that should give us a value of 0.01272 moles of oxygen. Okay, so we need to have mass to determine the nitrogen and or the oxygen, or both. If we are doing this, we need to have mass for those. But we need to have moles in order to determine the empirical formula. So now we're going to come back and we're going to look at moles of each one of these. So I'm going to write down each one of the moles. So for carbon, we had 0.05093. For hydrogen, we have 0.0648. For nitrogen, we have 0.02545. And for oxygen, we have 0.01272. Now, oxygen is the smallest amount. We divide each one of these by the smallest amount. So 0.01272, that's going to give us a 1. 0.01272, that should give us a 2. We should end up with 5 hydrogens and 4 carbons. So our empirical formula is going to be C4H5N2O. Okay. It's a pretty lengthy process, but we ended up getting that. So again, we need to know mass and moles, and use those moles in order to determine the mole ratio to get the empirical formula. Okay, the second question we're going to look at is similar to a gravimetric analysis lab that we generally do in class. And so we have this set of data, and we're given an equation. And so we want to go ahead and go through and analyze the data. So the first thing it asks us to do is calculate the moles of calcium carbonate. And so we can see that was a precipitate that we ended up forming, and we used that and filter that out in order to determine what our unknown is. initially on this side, which is the MCO3. So the M2, that's our unknown metal carbonate, okay? So unknown group 1 metal, and so we want to determine what that is. So the first thing I have to do is I have to determine how much mass came from the calcium carbonate. So we will do that by comparing these two. The filter paper, we want to subtract that part out of the total mass here. So we're going to have our 2.436 grams. We're going to subtract from that the 0.598 grams, and that's going to give us our mass of calcium carbonate, and that should be 1.838 grams of calcium carbonate. Okay, now that's not in moles. We want to know moles here. So for the second part of this, we're going to go ahead and convert into moles. We're going to use the molar mass of calcium carbonate. I'm going to go ahead and again round this value. It's approximately 100 grams for every 1 mole of calcium carbonate. And so that gives us 0.01 0.838, okay, moles of CaCO3. Okay. Now the next question asks for the moles of the unknown, and I like to do this in here. I know they're a one-to-one relationship. You might not see this question. You might be expected to just infer this some of the time, but I like to see this because I want to make sure we understand the mole relationship, especially at this point in the year for AP. So we have 0.01838 moles of calcium carbonate. And we can go back up to our original question and we see the relationship is a 1-to-1, okay? We assume a 1 at the beginning of those. And so we know for every 1 mole of calcium carbonate, there's 1 mole of the unknown carbonate, M2CO3. Okay. And so again, that value is going to be the same, but I want you to understand why it is the same value. So again, there may be questions similar to this that show up at some point that you would be expected to infer that. Now that we have the moles of the unknown carbonate, we can determine the molar mass. And so we were originally given a mass, or we had an experimental mass of 1.972. So we're going to plug that in. And then we're going to divide by the moles we just got to find our molar mass. That's grams per mole. That's the number of moles we had in the sample. So 1.972 grams of M2CO3. And we're going to divide that by 0.01836 moles of M2CO3. And when we do that, we end up getting a value of 107.3 grams per mole. So then the question becomes, all right, if it's a group 1 metal, that means it's going to be potentially lithium, sodium, or potassium. And so to be able to compare these, we want to know the molar mass of each one of these. I'm just going to go ahead and write them down. If you need any assistance with that, please let me know. So we have lithium should be approximately, I'm going to round to the whole number, 74 grams per mole. Sodium carbonate is going to be around 106 grams per mole. And potassium carbonate is 138 grams per mole. So then it asks, what's the identity? Well, what's going to be the closest value? We have to compare what we got experimentally to the closest thing. And so that means it should be sodium carbonate. Na2CO3. And whenever you see justify your answer, you have to explain how you know that. Okay, so the experimental value was closest to the molar mass for sodium carbonate. And so you would want to explain that in your own words. All right, for percent error, and I know I didn't carry all of those decimals through with me, so I might be a little bit off, but we should still be relatively close if we're rounding to the whole number. So what we want to do here is we want to go ahead and take the known molar mass, which was 106 grams per mole, and we're going to subtract from that the experimental of 107.3. And we're going to divide by the actual 106 and then multiply by 100. I put the straight lines there to show this absolute value technically, and so we should get around 1.3%. All right, one more problem to go. This is determining an unknown using Beer's law, or the Beer-Lambert law, by creating a standard curve first and then doing some analysis. So let's go ahead and take a look at this. So we had an alloy that had copper in it. We dissolved that alloy and we tested it against this standard curve. And so the standard curve was made using dilutions of known values, known molarities. And so what we want to do in this first part, it tells us that we have a 2.94 gram sample of the brass, which was the alloy, and it was diluted to 100 milliliters. We want to know the experimental process for that dilution. And so this actually came up on the 2021 AP exam, the first administration of the test. And so what we want to use is we want to use a volumetric flask, which is what we do in the lab. Okay, so this is a volumetric flask. This is the fill line, and this is a 100 milliliter mark precisely. Okay, so we use a 100 milliliter volumetric flask. And we place our sample. So here's kind of the outline. So we're gonna, place dissolved Cu2 plus ion sample in the flask. We actually do a variety of rinses in class when we do this lab. The second part is we're going to fill to the 100 milliliter mark with distilled water. Okay, DH2O is my shorthand for that. And then finally, we're going to cap it. So 3, we're going to cap. There's a little cap that goes on the top of this, okay, to seal it off. And then we invert several times to mix. Okay, so just a little lab technique there. All right, now let's do the analysis now that we have the technique down. So the first one says determine the concentration of copper ions if the absorbance for the brass solution was 0.800 for absorbance, okay? So here's what we're gonna do. We're gonna go on the absorbance side, so make sure you're on the absorbance side. And we wanna go up to 0.8. We're gonna go all the way over until we hit our standard curve line, and then we wanna drop that line down and we wanna read this from the graph. And I'm gonna say it's approximately 0.32 molar. Okay, there's an approximation that we can have that within. So then for the next part of this, it asks us for moles. Now, we diluted that sample to 100 milliliters, and so we have to go ahead and account for that. So we have to take the 0.32 molar, okay, and that's equivalent to 0.32 moles per liter. So molarity, capital M, molarity is moles per liter, and we have to consider that dilution that we did. So I'm going to take the 0.32 moles per liter, and I'm going to multiply that by the liters of the solution that I had. And so the solution that we had was 100 milliliters, and in liters, that would be 0.1 liters, okay, or divide by 1,000. So we're going to multiply this times 0.11 liters. Liters are going to cancel, and we're left with moles, and this is how we can determine the number of moles. So let's go ahead and do that, and we get 0.032 moles of copper that were in the sample. All right, the next thing, it asks us for the mass of copper in the brass. So if those are moles, we have to multiply by the molar mass of copper. So 0.032 moles of copper in the sample, okay, from the sample, and we're going to multiply that times the molar mass. So for every 1 mole of copper, we know there's 63.55 grams of copper. And this is going to give us the mass from copper that was in the sample. Let me see. Oh, it's on a different page that I have here that I pre-calculated. I got, with sig figs, it would be 2.0. I think I got like 2.03 something grams of copper. Box in my answers here. And then the last step, it asks us to determine the percent composition of the copper in the brass. And so for this, we're going to take that 2.0 grams of copper, and we're going to divide that by the original mass of the sample. So we have to go back up, and we are going to grab this number right here. Okay, so we're going to divide it by the 2.94. So divided by 2.94 grams of the sample, and then multiply by 100, and we should get around, I didn't round my previous number when I plugged this into the calculator, and I got 69.2%. Okay, if you put in just 2, it might be just a slight bit off from that. Okay.